All right, now number 2, OceanComm, Tom Riedel.
Good morning, everyone. So I'm Tom Riedel. I'm the CTO of OceanComm. We develop high-speed wireless communication for underwater. Think Wi-Fi for underwater. You can see here in this illustration of what it looks like today to deploy ocean equipment and how to connect it back to shore for onshore control. So if you have equipment on the water surface, it's fairly straightforward. You can use a satellite connection to get the information off these surface assets back to shore. Once you have assets deployed below the water surface, it gets a lot more difficult. Essentially, you have either a very slow wireless link. Those links today that you have available, they can send about 1,000 bits per second, or as an example, it takes about an hour or 2 to send a single image. If you want to do anything real time, so if you want to bring back data in real time from an underwater sensor, or if you want to do any sort of real-time control of an underwater robot, or even video streaming of an interesting site, you got to wire things up. Those wired links, they work underwater, at the same high speeds they work on land. The issue is they are very expensive to put out there. In a lot of cases, you would go out with a fairly substantially sized ship and then lower a cable down to the ocean floor. And having a station-keeping capable ship that can be safe hundreds of miles offshore is very expensive. They cost about $100,000 a single day, and needing to provide this kind of expensive infrastructure to make communication possible is just a pretty big barrier. What we have developed is a very high-speed wireless technology. It uses you can see what the prototype looks like. It uses very high-frequency sound waves, and it allows you to do things that today you can only do with these tethered systems, but you don't need any of the expensive support infrastructure. If you want to deploy these modems, they're 8-inch long in a pressure-resistant housing. If you want to deploy multiple of those, you put one on an underwater vehicle, for example, or a sensor. You can put another one on a buoy or an underwater observatory or hotspot, and then they all get connected with each other wirelessly through high-frequency sound waves. And we can enable video streaming, remote control of underwater robots wirelessly. That's something that's not possible today. If you look inside this box, you see high-end electronics borrowed from the medical ultrasound community. They already use very high-frequency sound waves, and then proprietary signal processing algorithms that run on this embedded processor on there. This graph kind of shows you the basic capability envelope of this system. It's a typical data rate over distance plot. So over short ranges on the left, we can achieve very high data rates on the order of megabits, similar to Wi-Fi. So over ranges similar to Wi-Fi, over a few hundred feet, we can get Wi-Fi-like data rates of a few megabits, which is why I say think Wi-Fi for underwater. It's kind of a pretty close equivalent, but capable of operating underwater. And then if you pull those two nodes further apart and communication distance goes up to 1 kilometer, 2, or even 10 kilometers, data rates do go down, but they gracefully degrade. And this is a technology we have tested extensively in the Pacific Ocean, Atlantic Ocean. We're not alone in this space. There's, like I said in the very beginning, there are other wireless solutions out there. just before I dig into some of the details here, on a very high level, there's 3 technologies that you can use for wireless communication underwater. You can use radio waves like on land, but essentially you'll be microwaving the water so that those waves don't propagate very far. They just heat up the water. And what you end up having is a very power-hungry link that has a range of a few meters, so nothing that's really practical. That's why I don't even have it on this slide. But acoustic communication is the most popular option. Sound waves propagate pretty well, which is why whales and dolphins use sound for their communication. So there's companies out there that use acoustic waves like we do, lower frequency acoustic waves, but still acoustic. The main difference is they're much lower data rate over the short range, the Wi-Fi kind of range of a few hundred meters. We've increased data rate by about a factor of 1,000. If you go a little further out, the gap closes a little bit, but it's a pretty substantial improvement still. The third technology that you can use on the water is optical communication. So you can turn a light on and off basically to signal a 0 or 1. That technology is very high speed over the short range, but it has issues with range. So usually you don't get more than 10 meters or a few tens of meters. And if the water is turbid or there is ambient light that interferes with the light sensors, then range can be actually a meter or less. So there's a range issue with that technology. All in all, we have an acoustic communication technology similar to other acoustic companies, but higher frequencies, and it allows you to do things like video streaming and remote control of underwater robots that today you can only do with a tether. Our initial target market are autonomous underwater vehicles, or the communication for those vehicles. Today, an autonomous underwater vehicle is a vehicle that's already wireless, but that also means it doesn't have communication capability. Essentially, well, except for this rudimentary capability of 1 picture per hour. So no kind of real-time communication capability. So the reason why they're called autonomous is because the way they are used is you pre-program them ahead of time. You tell them what lines to fly and what to do exactly, and then you submerge them and let them do their job, and when they come back, only then you really see what they have done and whether they have done anything useful. So the issue with these vehicles is they are fairly unreliable. About 10 to 20% of the missions fail. So you would pre-program them to do something, and then 10-20% of the time they are not able to accomplish what you have pre-programmed. And on 1% of the missions, those vehicles, they make the wrong decisions, they operate autonomously, and then they get lost completely, and you've lost a piece of gear that can cost hundreds of thousands or $1 million. So that is the issue with these vehicles, and the reason why we think our technology is appealing to the manufacturers and operators of these underwater robots is we can allow human-in-a-loop control. So you can bring a human into the control loop. If a mission goes awry, a human can go in and fix it. That's one. Another thing is most underwater vehicles still look like the ones that you see on the bottom there. So they're like torpedo-shaped vehicles that collect data like a Roomba. The newer vehicles look more like what you see on the top right. So that essentially these manufacturers try to break into a much larger market, which is the tethered robotics market. So this market is about $1 billion market. The tethered robotics market is tens of billions of dollars, and they're trying to get into this market because obviously once you have manipulator arms and real-time control, you can do work underwater, which is a lot more valuable than just flying lines and do observational work. Those are our value propositions to these AUV companies. The market grows pretty quickly, mainly because these vehicles are a lot cheaper to operate than a tethered robot. You don't need the surface vessel. So it's a pretty quickly growing market. In 2020, it's predicted to be about $1 billion. In terms of go-to-market plan, we will proceed along 2 avenues. So to push this technology into the defense sector, we work with the U.S. Navy. So we are on a contract with the Navy currently since 2016 actually, and we are taking this technology we've developed, this high-speed wireless communication capability, and we add an additional feature that would allow them to communicate clandestine. So essentially you can deploy these underwater drones, and then you can control them and have real-time feedback from them without an adversary noticing that these vehicles are there or communicated with. So that's something we're doing with the military sector, and then there would actually, this additional feature we're developing is it's going to be an additional standout feature that we have and other wireless communication companies don't. The second avenue that we are proceeding along is our partnership with MBARI to push this technology into the research sector. MBARI, the Monterey Bay Aquarium Research Institute, is a fairly large nonprofit oceanographic research organization. The objective of this collaboration is to enable large-scale ocean monitoring, much larger scale than what's possible today. And then with these dense data sets that you can then collect with these large-scale monitoring systems, you can drive better ocean policy making. And this is, I think, what aligns pretty well with the UN goal on putting better regulations in place for the use of ocean resources. This is a pretty wordy slide, but there's a couple quotes I found that I want to share with you because I thought they were pretty insightful, and because I thought they are really hitting the issue, the nail on the head on this issue. So the first one is by Chris Sholin, President and CEO of MBARI, the institution we work with for the research sector, and he wrote in a recent New York Times article that careful stewardship of the oceans based on data and not just the potential for short-term profit should drive ocean policy for fishing and mining. So it's, that makes sense. You want to drive your decisions and your policy making based on good data. But the question then becomes, what kind of data do we need and what do we have today? And that's what the second quotation discusses. It's by Art Baker, professor at MIT for ocean engineering. And he says, for many decades, the observation of various ocean processes were sparsely sampled temporally and spatially, leaving many processes not well understood because of the transient and regional nature of the data. So essentially, the data sets we have of the ocean are just very sparse. We don't have a lot of data. It has to do with the expense of performing data collection efforts on the ocean. So we have a very sparse set, and in a lot of cases, not enough to make solid conclusions from. So the solution to this is obviously to really scale up our ocean monitoring capabilities, to really build a large-scale system that can measure the significant ocean health indicators for overfishing, marine pollution, ocean acidification, etc. So this is what we're working on with MBARI. It's a large-scale ocean monitoring system. Before I talk more about the solution, maybe a few sentences on how most of the data collection is done today. So today, if you want to collect data on the water, you would go out with a ship, a research vessel, a manned research vessel. Like I said, ship time is pretty expensive, but you go out there, you deploy a sensor subsea, you leave that sensor there for some time to collect data and store the data on a onboard hard disk. And then you come out later, maybe a few months later or even a year later, and then you pick up that sensor and you download the data. So a physical retrieval to get the data back. So this, having to go out with a boat for the deployment and retrieval of the sensor makes it very expensive. The idea here is to get the data off those sensors without any ship time, without the mobilization of a ship. So what we're going to do instead is you have these sensors on the water, and they will be outfitted with a wireless modem, and they can then send their data or upload the data in situ to a surface buoy above. For example, this mobile buoy that you see here, a wave collider hotspot. So they upload it there, and then from there you have a satellite link that ties it back to shore, and you have this data available without any sort of ship mobilization. So this technology will bring down the cost for large-scale data collection by about a factor of 10, or in other words, for the same research budget, you can scale up your efforts by a factor of 10. In our MBARI partnership, we're developing a pilot, and the Neptune Round prize money will be used to fund work on this pilot. Maybe a few sentences on how we got here and where we are. So I've been working on this for about 10 years now, and First as a researcher at the University of Illinois, and then worked with my PhD advisor Andy Singer, who is also co-founder of this company. And then in 2014, 2015 is when we started the company to commercialize the IP we have developed jointly at the university for about 10 years. Andy Singer has pretty significant history in underwater communication. He was part of the team that deployed the initial wireless capability to the US submarine fleet as part of his work at Lockheed Martin. He worked also a little bit on it as a grad student at MIT, but then really focused on it right after at his job at Lockheed Martin, and then became a faculty member at the University of Illinois where I met him. Last slide. This is our progress to date. So we are not venture-backed. We have bootstrapped this company first with grants from the National Science Foundation. That's how we got started in 2014, 2015. And then as the technology and the feasibility of it was established, we were able to win some contracts with the US Navy, and starting 2016, and we've been able to grow the company from there. The Navy has really liked our work so far, and we have done a couple of ocean tests with our technology that impressed them. So we are working on 2 additional contracts with them, and a demo in 2020 for essentially a pilot system. And then for this prototype I showed earlier, we're working towards getting this this most basic version of this modem out the door to the commercial sector next year, and we have received pretty good interest so far for this device from a set of companies in different sectors. And I look forward to a lot of modems next year when we kick off sales. Thanks.
Great job. Good. Questions? So the effective depth is about?
Depth doesn't matter.
Okay. It's the distance to the water, though.
Yeah, so if you need more depth, the housing may be more expensive because the pressure is higher that this housing has to withstand.
Got it.
But the distance between the 2 adjacent nodes that you want to talk to is what matters in terms of data rate.
So you could have adjacent nodes pretty far below the water talking to each other as long as they weren't too far apart.
Yeah.
So I love it. It's a networked ocean.
Exactly. Digital ocean.
Yeah. Question over here.
Go.
Hi, Tom. So your performance improvement of essentially 2 orders of magnitude. Arguably, you're not breaking the laws of physics, but you've got some really good lawyers there, right? I mean, you're really on the edge of what physics tells us is achievable in acoustic telemetry. Could you comment? Because you didn't, and I've been in the space a while. I'm trying to understand: is your differentiation based on hardware processing, your signal processing, like just from a little bit in there of how you're getting to that dramatic improvement? To the extent you can reveal it, would be really appreciated.
So I anticipated that question, which is why I have this slide. So it's not the physics are actually pretty clear. Over ranges of a few hundred meters, you have hundreds of kilohertz of acoustic bandwidth available, and that's also commonly used for very high resolution sonar systems. So you have hundreds of kilohertz, even a megahertz of acoustic bandwidth available over the ranges where I'm saying we can get a megabit, so hundreds of meters, Wi-Fi-like ranges. Then if you look at modern wireless communication technology, like you have in your cell phone or Wi-Fi, you can get several bits per second for every hertz. So now if you take the bandwidth number and multiply it with that, with those common spectral efficiencies, then you actually get these numbers. It's pretty, any sort of high-level analysis would guide you to these numbers, really. The issue why the performance gap is so big is those modems you can buy today, they really haven't changed for 30, 40 years. They use some very basic technology called frequency shift keying, where you send a low frequency tone, a high frequency tone, one is a 1, one is a 0. It works very robustly, it's very simple, doesn't take a lot of processing, but it's also not very fast. And the spectral efficiency, so how many bits you can pack in every hertz of bandwidth, is very slow with that technology. So that's number 1. Then number 2 is we use higher frequencies, so we really leverage the bandwidth that's available over the short range. Existing modems where the technology development was driven by what the Navy wanted 30, 40 years ago, which is very long-range communication, so it didn't even really look at the shorter ranges in the first place, and also not at the higher frequencies. And then there's a third component that's fairly unique, and that's it's specifically what we're working on with the Navy. Once you go to these high frequencies, you can build very small arrays. We're talking wavelength of a centimeter or less. So you can pack an array of 10 or 100 elements in this kind of form factor, and then you can focus sound, similar to how a laser focuses light. So we can, even though it's high frequency, and higher frequencies attenuate more quickly than low frequencies, we can power boost by essentially controlling or beamforming or focusing this, where the sound goes, and then also at the receiver we can really kind of listen in on where the sound comes from. So there's a power or range gain even for those high frequencies if you do that. Yeah, so that would be probably the biggest points.
Okay. Tom, on this side?
Yeah, hi. I'm more familiar with the optical comms, and I think your numbers might have been a little low, but what I'm interested in is, do your algorithms, I got that your hardware seems pretty unique from the medical imaging, but the algorithms, do they take into account parameters in the environment? Are they adaptive at all? And can they do any kind of mesh networking, perhaps in a swarming type pattern?
Oh, they're very adaptive. So they also the slide that was up there actually mentioned it on one of the bullet points. So so to really pack this much information into the bandwidth that's available, you need to use coherent signaling. I don't want to get into details, but basically, in order to make that possible, you need to track things like Doppler and the vibration and the echoes that exist in the water. You need to track that basically on a microsecond level. And we have machine learning on this modem that essentially understands the physics of how things are moving around and what acoustic wave propagation looks like underwater. It takes that into account and then predicts it and estimates it. And we use that information to undo any distortion that we'll see in the received signal to then retrieve the original information from the transmitter. Yeah, so it's highly adaptive. Yeah. Mm-hmm.
Jane?
So I'm wondering about three different aspects of what you mentioned, because it's full of I'm full of ideas based on how rich a proposition you're offering. So one of them is echolocation in animals. Have you been doing any testing to see whether there could be any interference with echolocation on the part of whales and dolphins on account of the waves that you're propagating?
Yeah, I get that question a lot. So so in terms of us bothering marine life, to address that first, we operate at much higher frequencies than what marine life uses. Whales use very low frequencies because they want to cover hundreds of miles in terms of distance. So they use in the hertz, we use hundreds of kilohertz, so much above what they use. The dolphins are the mammals that use the highest frequencies of, as far as I know, and they are a little bit below basically where we operate. So we're right above basically what they can hear. Similar to how medical ultrasound doesn't bother your ears because it's too high frequency. So that's one. And then I don't know. This brings up another interesting point in terms of what bothers our equipment, because we are actually very low power, and even if we were to operate in the same frequency as whales and dolphins, they send out much louder signals than we do. For us, the point is to have these modems very low power, so they can stay submerged for a very long time. We only send about 1 watt in power, and the only interference that we usually pick up is by other sonar equipment. And then with that sonar equipment, it's very high power, but it's low duty cycle, and then we communicate in those gaps where the sonar system is not on, and that's usually 99% of the time. So then there's no problem.
So a very different question,
Yeah.
and then I'll stop, about application is, are there national security applications for what you're describing, and have you been exploring those?
In a way, the work we do for the Navy is national security. Yeah, so there's the Navy is interested in mine countermeasures. If if a Rouge state mines an area that's an international trade choke point, they want to be able with their allies to come in and clear those routes. So you want to be able to operate underwater very efficiently and clear mines and in very large volumes of water. Then, there's, I don't know. I mean, pure defense would then also be submarines and underwater drones and that kind of stuff. For what did you have specifically in mind? Like something closer to home?
Yeah, just can you use your technique in order to monitor where there are undersea vessels, for example, from other sovereign powers?
Oh, yeah. Oh, that actually brings up a good point. So we have been contacted by several port authority organizations. So they are worried about, so they have these large ports and there's very valuable goods flowing through. And they're worried that, the reason why underwater is interesting for the military is because it's so hard to do anything under there. Communication isn't working very well. You can't see really well. Sonars feel limiting. So you could, an adversary could also use that to compromise a port, for example. And what they want to deploy is essentially some sort of underwater sonar system that's where the sonar imagery is then fed back to the port authority to make sure. It's kind of like underwater security cameras, if you want. Yeah, underwater wireless security cameras.
Thanks.
Yeah, thanks.
Over here, Ann?
I'm going to switch gears on you to ask you to take a little bit of time to describe your go-to-market strategy, manufacturing, licensing, partnerships, whatever, to actually get this solution to scale.
So our company, in terms of manpower, is mostly focused on the electronics and the software. The software is proprietary, and that's kind of a key aspect of our IP. In terms of manufacturing, the electronics are fairly standard to produce. We do integrate high-end medical ultrasound components, but the manufacturing it you can outsource to turnkey manufacturers pretty easily, which is what we have done in the past. So we're based in Chicago. There's companies in the suburbs that can produce them on a very large scale for you. I would say the most important component that we don't manufacture ourselves is the piezoelectric transducer, and for that we have partnerships with multiple companies that produce them for example sonar systems, and they have designed a custom version for our needs for wireless communication underwater, and so that's the manufacturing side of it. In terms of scaling it up, I see going along the lines of the defense is certainly the largest aspect of this market today for these wireless underwater vehicles, and I think in my mind the way to do it is to have build these early relationships with the Navy, like we're doing now with these contracts, and they are a great sponsor of new technology, and they actually even allow us to use that money to build unique features that we don't even have yet, like this clandestine communication capability. So as we hit our 2020 demo, whose development work is all funded by the Navy also, that pilot is going to, or the demo is going to show what it can do to all the generals and possible users in the Navy, or actually admirals using the Navy, not generals, I realize. But then from there, we would then have go into larger delivery contracts, basically, once this demo has been successful.
Any other questions? Okay, Tom, thanks.
Yeah.
Great job.
Thanks.